swap out with you and stand where you're at, I guess.
Yeah. Hello, my name is Terry Lowry. This is Simon Oberchrome and Andrew Muha, and this is our project for the semester of Embedded System Design.
And so for our agenda, we have the abstract, introduction and background, our project objectives, mythology, project budget, and project timelines, and our conclusion. First off, on the abstract, we want to use an embedded system to design an adaptive greenhouse. We want to monitor humidity, temperature, and the soil moisture, and use these sensors to detect like the environmental changes within our greenhouse. They will actuate triggers and display necessary information to the user through an LCD screen. With the increasing market demand for local green and organic produce, there exists a greater need to grow a variety of crops in regions where conditions may not be optimal, requiring controlled environments and greenhouses. Maintaining proper growing conditions for crops is essential, as it creates greater yields and more profitability for companies. A solution to this comes from embedded systems, which allow us to have really solid feedback and control systems of the greenhouse itself and the environment around the plant. The ability for a user to monitor the environment and use actuators to dynamically control the growing conditions allows it to just have much better cost benefit. A little bit of background. Early example of microcontrollers is being used for controlling sprinkler systems in a grocery store, keeping produce fresh. More recent uses, China has an indoor garden which grows plants without natural sunlight or soil, all controlled by embedded systems. And controlled greenhouse systems are becoming way more popular just because they're more efficient and profitable. Our project objectives, first off, we want to design a routine which creates an optimal growing environment for agriculture. We want to break the process down into sequential and combinational logic and implement it in a software along with integrating it into a user interface. Third off, we want to design the actuator system and implement a sensor configuration that optimally uses the microcontroller resources. We want to create a test enclosure which can house the system in a plant specimen. And lastly, we want to test the viability of the system and adjust the parameters accordingly.
All right, so for phase one, the first step is to determine a routine to adjust the environmental conditions. And the first step in this is doing extensive literature review to find out what these optimal growing conditions are and how we can adjust them for what type of plant we are growing. Some of these conditions that we're taking into account are proper temperature and humidity regulation, or humidity conditions, along with sufficient water. So through extensive research, we'll examine their effect on growth and determine how they can be incorporated into the routine. Phase two is to logically break down the routine and implement it through code. So first, we will make a flow chart with all of the logic flow. This includes combinational and sequential logic and all the input variables and their effects on the outputs. Additional software will be required to integrate adjustable parameters into a user interface, which consists of the LCD display. Phase three is where we put everything together. And the first step in doing that is to design how the sensors will fit into the system. So we're using the temperature and humidity sensors to display information on the LCD board so that the user can monitor the conditions in real time. The water level sensor will be used in the water reservoir to monitor how much water is left in the reservoir, and also this will be linked to the LCD display to give a notification when the water needs changed. There's also a soil moisture monitor, and if the moisture gets too low or too high, the system will adjust the irrigation rate as necessary. Phase four is to build the system, and the first step in doing this is to build a test platform, which will have the water reservoir suspended above the plant specimen, and the water or the soil moisture sensor in the soil. We need to ensure that the water cannot damage the electrical components, so proper care has to be taken to insulate those from getting wet. Since water will passively drip into the soil, we don't need a water pump, and we'll just use a plastic bottle suspended over the plant to create a gravity-fed irrigation system. The final step is to test the system. So we will need to monitor the plant health over a period of time while the irrigation system waters it. We will then record any changes in the plant health and adjust the parameters as necessary.
All right, so for the budget, we'll only need a few things in order for this project to work. We're going to need an Arduino sensor kit, which will allow us to get access to all the sensors that we are looking for this type of project. Then we need a plastic bottle, which is basically free, which we will use to drip water into the plant whenever it is not watered enough. And then we will need a potted plant, which will cost about $3 roughly, and this will be the main test subject of our project, which we will be observing to see how it fares with the greenhouse irrigation system. Then we need a soil moisture system, which does not come in the Arduino sensor kit. And this sensor will be used to monitor the moisture of the soil to make sure that it will be able to tell the watering sensor when it can apply the water from the plastic bottle to the plant to water it. We'll need the DC servo motor, which is the actuator which will control the drip irrigation rate, which means that it will control, this will receive its signals from the soil moisture sensor to use the plastic bottle to drip the water into the soil. Then we need a jumper wire bundle, which will help for making the electrical connections between the system components. We've got a lot of them, and so we're going to need some wires to connect them all. And then lastly, we'll need cotton string, which will be used to suspend the plastic bottle above the soil. For our Gantt chart, we were going to have a few different steps, which will take some time. Our first two activities will be used kind of alongside each other, and will take about 2 weeks each. Firstly, we have to optimize the irrigation and lighting routine, which we will do by which we will first have to plan out the system and how we're going to implement it. And we need to implement the routine in code. So as we're working with this routine, we need to program it to make sure that it will work the way as it is intended. And then starting on week 2, we can then configure the sensor layout on the microcontroller to match the code and see how it works in tandem with it. Starting with that'll take about 2 weeks. And then starting week 4, we have a few different things. We can design the drip irrigation system, incorporate the system into the test fixture with a plant specimen, and then test the functionality of the system. All this sort of happens at once. It's all the design functions of the system, which will all need to be tested together because it's all part of the same system, which will be the end product. And then finally, we'll have to make the necessary adjustments. That will take about a week. Once we have the whole thing done, it should just be a matter of a few tweaks in code or how the system is laid out, which we will use to optimize it. And if the plant didn't get enough water, it will add more water, vice versa. It'll check the lighting better, and it will be fully optimized by the end of the project. In conclusion, adaptive greenhouse environments help to meet the delicate needs of cultivation. Yes, plants are much better when grown with optimal conditions. Even just having a little bit less or more water than it needs, having a little bit more could drown a plant easily, having a little bit less can make it not grow to be as good as it could be. We plan on developing a system which will monitor and display a plant's environmental conditions. This will cause it to be able to adapt to the environment around it, so that it can sort of be self-sustaining without the need for human intervention, or much human intervention. And then we expect to have a project which displays a plant's condition and controls actuators by the end of the semester. So this project will be using sensors to test different aspects of the environment, and then it will send it through actuators the signals that it needs to make the system work. All right, thank you very much.